Yes, I'm online. Yes.
In space sciences in the country, highlight past, currently ongoing, and future space science missions, and present important astronomy and astrophysics research being conducted around the country. The goals of this lecture series is to inform the public about national endeavors and enthuse students towards pursuing a career in astronomy, astrophysics, and space sciences, which is one of the most visible and successful domains of research activity in India, with multiple past successful space missions of ISRO, many future missions coming up, and our involvement in various mega science projects such as the 30-meter telescope, LIGO, SK. We are looking at a very exciting time ahead for astronomy, astrophysics, and space sciences in the country. So today's lecture is going to be given by Dr. Tirtha Pratim, who is the director of the Science Program Office of ISRO. Let me provide a brief introduction to the speaker. He is an alumnus of the Department of Physics, College, Calcutta, and the Institute of Radio Physics and Electronics of Calcutta University. His current responsibilities include taking forward the missions of ISRO towards the exploration of space and sow the seeds of new scientific endeavors through the Science Program Office. Dr. Dash started his career in ISRO in 2004 as a rocket technologist in Vikram Sarabhai Space Center, ISRO, in Thiruvananthapuram. Subsequently, he shifted to the Space Physics Laboratory at VSSC and embraced planetary sciences as his scientific career and earned his PhD for his work on the mobile gases in the lunar exosphere. He has played significant roles in the Chandrayaan-1, Mars Orbiter mission, and Chandrayaan-2 missions in multiple capacities, including project manager, payload scientist, and principal investigator, before he moved to the ISRO headquarters in Bangalore. Dr. Dash also handles the responsibility of initiating several disruptive and futuristic technologies for the space sector. It's a pleasure for us to have him inaugurate this lecture series with his lecture on space science exploration at ISRO. Tirtha, the stage is yours.
Thank you very much, Dr. Devendu, and thank you, Ceci, ISR, Kolkata, for this excellent opportunity. And I must say here, when I begin, today's lecture is meant for the dear students, so many of you may take space sciences as your career. So I take this opportunity to give you a broad overview of the space science activities which we have been doing, and I assure you that I should not go to the details of any scientific or technical intricacies in my lecture. This is not the purpose in this forum. So in this 45 minutes or 50 minutes journey, I will try to restrict myself to that time limit so that the interactions are happening at the end of the lecture. So let us begin the journey. I will share my presentation. So are you able to see the title slide?
Yes, your titles are visible and it's full screen.
Right. So when we think about where we are located, it is really amazing. It is bewildering to think that we are a small part of this gigantic universe. So when I was studying out of my own curiosity during my student days, I came to know that there are some about 2000 billion plus galaxies in this observable solar system. And in these billions of galaxies, we have our Milky Way, and in our Milky Way we have our solar system, and in the solar system we have a planet which is in any case in a very much favorable zone to host life, and this is Earth. So our presence in this gigantic macrocosm is really mind-boggling, and that is the fascination. That is where the fascination begins. Why we are here and how do we connect with the rest of the universe? Okay, so this is the basic motivation of space sciences. Now the question is, when we say space sciences, what does it really mean? So if you ask a person, what do you mean by space? Many people will come up with different answers. Okay, a person may say, okay, to me the space starts from the basic atmospheric layers. Earth has got different layers in the atmosphere that all of us are aware. And then when you go beyond a certain height, 90 kilometers, 100 kilometers, you have ionosphere, thermosphere region, and this we call the near Earth space. And then when we go beyond, we have the other planets and the natural satellites, the solar system in general, and the sun itself. So those are space, those are the celestial bodies which we are interested to study. And there is something beyond the solar system and even beyond our Milky Way, where there are different interesting elements for our study. Especially people are telling about, okay, we are in Earth, so much favorable in that Goldilocks region with the right amount of temperature, pressure, and all the factors that can sustain life. Whether there is something similar to Earth elsewhere, and wherein there must be some similar Goldilocks region which must be hosting some form of life, and we are not alone in this universe. So, okay, so it is always a quest towards the connectivity to understand the interconnectedness, as my teacher in St. Xavier's College used to say, the undercurrent of unity in everything. So that is the motivation of space science. Now the question is, seeing is believing, as people say. Can any one of you name, this is not an in-person lecture, this is the problem with virtual meetings. If I ask any students that can you name a great invention that expanded our horizon? We see it, so we believe. What invention did we witness that expanded our horizon? The answer will be telescope, which happened in early 17th century. So with the help of telescope, we started seeing whatever we could not have seen with our bare eyes. So we could see certain celestial objects, and as the light takes a finite amount of time to reach your eye, longer you see, you actually are seeing, uh, part of the history. So it is a time machine. Telescope is basically a time machine, which you are having. So this was a disruptive change in the observation, which was made by mankind of the sky, night sky. Now then, there was one more invention called camera. So if you integrate a camera with a telescope, you don't have to look at the telescope and draw a picture on a drawing board. You can take a picture of the through the telescope of the celestial object. So we call this the imaging of a remote celestial object. So that's how the increment in technology started happening. And then something more interesting happened. That is, the light which is coming from a distant star or any distant, not necessarily it has to be a star, any celestial object. Some light is coming to you which is carrying some information. Imaging is one part of it. But suppose you have a mechanism of resolving the different wavelengths of that light which is coming from the celestial object. We call it spectroscopy. And this tells you a lot of other information which a mere imaging does not tell you. Okay, so dispersion of light, and resolving different wavelengths of the light which you are getting from the celestial bodies started telling a lot more. And there, the different branches of observational astronomy emerged. Different parts of the this electromagnetic spectrum started telling some story or the other. Okay, if you see the visible part of the spectrum, which is very narrow indeed, it is 0.4 to 0.7 micrometer, which we can see with our bare eyes. So a lot of story were unseen. Now with this advent of these techniques wherein you can probe at the different parts of the electromagnetic spectrum, both at the shorter wavelengths and the longer wavelengths, the capability increased and a lot of things started unfurling. And every part of the electromagnetic spectrum had some story or the other to tell. As for example, I have compiled this kind of a table. Say if you have the gamma ray domain, it tells about accretion disk around the black holes or gamma ray burst. If you are looking at the X-ray regime, it tells you of the gas clusters of galaxies, supernova remnants, stellar corona, and also, last but not the least, in some other context, it tells about this X-ray. Don't think that it is directly light coming, X-ray coming is the only astronomy you can do. If you are looking at a planetary surface, and if the solar radiation excites an atom there, and if the atom de-excites, giving rise to some X-ray photons, that also tells you some composition information on the planetary surface. So that is another way of looking at the whole thing. Then coming to ultraviolet, ultraviolet domain tells a lot of things about supernova remnants, very hot stars. Also, it tells, in the same way which I have explained, atmospheric composition of planets. So the emission which are coming in the ultraviolet region from different atomic transitions, they tell you about what are the atoms and molecules present, in the planetary atmosphere. Then you go to the visible wavelength, you can study the planets and natural satellites, the stars. And then you go the infrared region, you can study the cool clouds of dust and gas planets. You go to the microwave region, you study still cooler objects and also the microwave background radiation. And if you go to the radio waves, you see a lot of dynamics of charged particles like electrons in the magnetic field. So these gave rise, as I tell you, different branches of astronomy, and also a very good technology took birth from here. It is hyperspectral imaging technology. If you have access to different wavelengths and also you integrate the imaging technology with it, you can tell a lot of stories referring to different channels of your instrument, which are catering to different parts of the electromagnetic spectrum. Now, as I was telling you, if just ask somebody what does person mean by space, you will get many types of answers. Now, since the time is short, I will cut it short and come to the point. See, there is a line called Karman line at 100 kilometers above the mean sea level from the Earth's surface. So some people tell that, okay, whatever is coming above the Karman line is your space. Okay. Karman line basically is a line of demarcation between aeronautics and aerodynamics. But if you ask somebody who is very much bothered about what is happening right from the Earth's surface, which we call the atmospheric boundary layer and above, okay, then they will say my space starts right from the surface of the Earth. Okay, so there is no hard and fast definition. It depends on the context which you want to study. And here at this juncture, I should tell you, if you have to access space to study, what are the techniques available? You have balloons, but balloons can take you up to some 30, 20, 30, 40 kilometers. Then you have sounding rockets. Sounding rockets can take you obviously below, above the Karman line, 100 kilometers and above it can take you. Nowadays we have in India our sounding rockets which can take you to about 500 kilometers. But the problem with sounding rockets is that you can access the space, but you cannot stay there for longer. Okay. So you have exploration with satellites. Satellites allow you a prolonged access to the space. And that is how, if I have to tell you, the seat of the space exploration program in India is indebted to two major facilities. One is the National Balloon Facility of Tata Institute of Fundamental Research, Hyderabad. You can see a picture in the right-hand side top panel. And also in the bottom panel, which I'm showing, the Tumba Equatorial Rocket Launching Station, TERLS. Okay, so one was by Homi Jahangir Bhabha sir and one by Vikram Sarabhai sir. So these two were two pillars of the National Space Program. Now, if I have to tell you a very short story before I rush into the description of the space program, what is happening right now. As I told that we didn't have to wait for the formation of rockets or satellite technology to start doing space sciences. How can you do space science? You can do mathematical modeling, you can do a lot of physics, and you can do some observations of space. So it was in 1940s, the foundation of space science in India really happened with a set of cosmic ray experiments from balloon platforms from the Tata Institute of Fundamental Research National Balloon Facility, which could take you to an altitude of 30 to 40 kilometers from the Earth's surface. And these kinds of experiments continued, mostly based on the cosmic ray experiments. And in between 1960s to 1980s, that 2 decades, witnessed the studies on hard X-rays. So when we say hard X-ray, we mean the X-ray photons which are having energy more than around 20 kilo electron volt from the sum of the bright X-ray sources in the sky, again from the balloon platform, and thanks to the scientists from the Physical Research Laboratory, Ahmedabad, and Tata Institute of Fundamental Research. So they contributed tremendously to this experiment. So not only the cosmic rays, X-ray astronomy also took its birth. And something fantastic happened in around 1960s when the sounding rocket platform was made available. And that was the beginning where sounding rockets used to carry experiments of two types. One is the X-ray experiments, and another set of experiments on upper atmospheric science. And that time we used to have launches of sounding rockets from a place called Tumba, which is near Trivandrum, Thiruvananthapuram, and Sriharikota. You know Sriharikota, where from the big rockets are launched currently. So during this time, the cosmic sources in about 1 to 10 kilo electron volt energy is to be studied. And at the same time, the Tumba, where from the sounding rocket sounding rockets were launched, that place is known to be at the birthplace of lot of scientific theories on the upper atmosphere. Like lot of observation happened on the ionospheric dynamics at the magnetic equator. So as you are aware, the magnetic equator and the geographical equator are not coincident. The magnetic equator passes right over the Tumba, and Tumba also is at the coastline, west coastline of the Arabian Sea. So you can always have a rocket launched from it, and you can access the space right of the geomagnetic equator and study different phenomena like equatorial electrojet and counter electrojet, equatorial spread F, to name a few. So that was the time when, in 1963, this Tumba Equatorial Rocket Launching Station was uh, founded, and a lot of experiments happened from the foreign countries as well. And in 1969, ISRO was born, and Tumba Equatorial Rocket Launching Station was dedicated to the United Nations. And at the time, in Trivandrum, there was Space Science and Technology Center, STSC, SSTC, Space Science and Technology Center, and which later was renamed in memory of the father of the Indian space program, Vikram Sarabhai, as Vikram Sarabhai Space Center. And there we had the Space Physics Division, SPD. SPD used to be very active for this upper atmospheric research with sounding rockets. And later on, SPD grew as an independent laboratory under Vikram Sarabhai Space Center, and it became SPL. So that was the beginning. And now the thing progressed in this way that people used to start feeling a deficiency that you are having sounding rockets to launch, but sounding rockets cannot stay there for longer. It goes and then it comes back. So if we have to have a prolonged access to space, there should be some satellites. Now that was the beginning when the hunger was getting developed in the scientific community, and that was the birth time for the first Indian satellite, Aryabhatta. And all these instruments which were developed for the sounding rockets, whether it is for the X-ray astronomy, whether it is for the cosmic ray experiments, all these were the training grounds for the then Indian scientists to develop instruments for satellite-borne experiments. As many of you can guess, that it is not easy to develop instruments which are going to work on space as well. Your instrument can work on the ground, but not necessarily it may work reliably in space. So that was the training ground. Now then, the situation changed. So Aryabhatta was the first rocket, not rocket, the satellite from the Indian soil, which flew with X-ray astronomy instruments, also containing some astronomy instruments and solar physics instruments, but it was launched using the Cosmos 3M rocket in 1975. And that was the time when, around 1987, which I have not shown here, the SROS series of satellites started taking birth in India. And this series of SROS series of satellites contained some gamma ray burst experiments. And in 1992, the SROS-C was flown in Augmented Satellite Launch Vehicle ASLV, which was containing some gamma ray burst and retarding potential analyzer experiments. And you must notice here, as I have shown you a timeline, I have marked the major missions of space science flown by our country. In the bottom panel, I have also shown here how did our launch vehicles evolve. So if I have to go through here, that this SROS series of experiments, when it was successful, that was the time, contemporary time, when NASA launched the Compton Gamma Ray Observatory. But that was also not a killer of the motivation of the Indian scientists, because globally there was an interest to study all these celestial objects, and the Indian scientists also thought that, okay, let us continue working towards the national capacity building, towards making space-based instruments and doing science out of it. Now, success of these indigenous GRB experiments inspired TIFR and ISRO for coming up with an idea of X-ray astronomy experiment on board an Indian satellite. And that was the birth of the experiment called Indian X-ray Astronomy Experiment, IXAE, and which I have shown here, 1996. And it contained X-ray astronomy instrument. I am not going to the details of this because of shortage of time once again. It yielded many fascinating scientific results, and in between, people have started thinking that, okay, this success should lead to a dedicated astronomy payload of India. and we should make use of different parts of the electromagnetic spectrum to look at the sky. It should be a multi-wavelength eye of India to do astronomy from space. That was inspired by the success of IXA, and that is how the seed of AstroSat was sown. And okay, in between also many significant things happened, like SOX instrument was flown in GSAT-2 satellite, which is a solar X-ray spectrometry experiment. Then it was flown, in PSLV, in different configuration of PSLV. And then there was a time when, it's 2008 time frame, when we ventured into a new domain called planetary exploration. So this planetary exploration, we started with Chandrayaan-1, and then came the Mars orbiter mission in 2013, and then the AstroSat became a reality in 2015. And then, in 2019, we had our mission Chandrayaan-2. So this is how we evolved in the launch vehicle capability, starting from SLV-3, ASLV, PSLV, different variations of PSLV rocket, GSLV Mark II, and then GSLV Mark III. And at the same time, with the increase in the capacity of launch, we started exploring different domains, not only the astronomy, astrophysics, also solar physics, and also planetary science. That's how we progressed. Now, if we come to the major themes or major verticals of the Indian space program, the major verticals I can classify in this way: planetary exploration, wherein we focus on the moon and Mars currently, but there are other planets also and natural satellites to be explored. Planetary exploration does not mean only planets. Okay, it is a very generic term. It also includes the natural satellite, like moon, and also it is also including the small solar system bodies like comets, asteroids. Then we have heliophysics and space weather studies, including aeronomy. Aeronomy is the study of the upper atmosphere, physics and chemistry of the upper atmosphere of the Earth, especially the ionosphere, thermosphere region. And astronomy, astrophysics, which includes the exoplanets. Now, you do all these things basically with a two-pronged approach. One is you do theoretical modeling. And when you do theoretical modeling, you do a lot of physics and chemistry. That is one approach. And there is another branch of modeling called AI/ML based, artificial intelligence and machine learning based modeling. Basically, it is a big data analytics inspired technique wherein you don't bother about the physics. You search for the patterns, some occurrences by crunching huge data and find out what is happening. And this is now bridging with today's physics-based modeling, and a lot of insights are coming because of this pattern recognition by the AI/ML techniques. And obviously, there is another prong like observations. When I come to observations, there are ground-based studies with atmospheric radars, ionosondes, GPS receivers. Many of you are aware of different techniques, and also the space missions, wherein you have observations made from the space. Now, many students have asked me, how does a space science mission take its shape? So to you, I have this table, this flowchart, which tells you, you start from a fundamental question. And that fundamental question, it is something like this. Fundamental question can be, how did the solar system evolve? Very big question. Now you split up the fundamental question into a set of specific questions and you set your target. If you set your target, means you set which celestial body you want to study. And then you identify the domains, what you want to study, like whether you want to study the surface of the planet or the interior of the planetary body or the atmosphere. I am telling in the context of a planetary body, but whatever I am discussing is valid for any astronomical object also. So the context only will change, but fundamental steps remain unchanged. And then as a fourth step, to define the exploration platform. So gradually, from your wisdom, you are going to science. From your science, you are going to technology. You are defining your instrument, what the instruments you should fly. You are developing the instrument specifications, generating the specification table, and also you are thinking which experimental platform you should use. Like when I'm telling different exploration platforms, what do I mean? What I mean is whether you will fly your experiment in a balloon, if you have to, if you're okay with probing 30 to 40 kilometers above the Earth's surface. If you're not okay with that, you can think of sounding rockets, which can probe higher altitudes, but there you are not going to get access to space for a longer time. Then you have to think about satellites, okay, which will definitely give you longer time access to space. Satellites not only around Earth, you can think of satellites around any other celestial body like Moon or any other planet. If you want to study the surface of the celestial body, you can think of landers and impactors for the surface studies. And if you have to think about impactors, there's a special kind of impactors. There's a special kind of landers, which are called soft landers. Like when you are landing, you should survive after landing to do some science. Impactors are also important when you are trying to perturb the surface and trying to see the effects of the perturbation which you have created from some other platform. So these are the techniques, and also you may have to have rovers. So simply landing is not enough. You have to rove around to study different positions of the surface. You may also envisage flyby missions, wherein the spacecraft passes close by a celestial body and conducts specific scientific observation. And also you can think of space observatories, like the observatory, you can it is launched to space to observe celestial bodies and astronomical sources, like the way you're having the Hubble Space Observatory or the solar observatory, which we are planning, like Aditya L1 from the first Lagrangian point, around the first Lagrangian point in a halo orbit. So these are kinds of exploration platforms which we have. Now, exploration platform is one aspect. Then you have to come to the instruments. So what kind of instruments you would like to have in your mission? So there are two techniques again. You can do remote sensing, wherein you study the subject from a distance. You can study with respect to the radiation which you are receiving from the celestial body. As for example, reflection and scattering of the solar radiation which is coming from a planetary surface, and analysis of the reflected signal. So this can give rise to, again, two approaches. One is spectroscopy for the analysis of the spectral absorption features, which can tell you a lot of things about the composition. Also imaging. There is another technique in remote sensing, wherein, as I have told, solar radiation is incident on the surface and it is causing excitation of the atoms. The atoms are undergoing relaxation or de-excitation, and they are emitting some radiation out of this process, and that radiation you are capturing. These are all remote sensing. But remote sensing, I should tell you, is not necessarily that it has to be a photon remote sensing. Remote sensing is also possible with respect to particles which are coming. Like if you're having some energetic neutral particles which are scattered from a surface, planetary surface, and you are analyzing those sitting at a distance, it is possible to backtrack those energetic particles and tell where from they are coming, and you can map this information on the planetary surface to understand what is happening. Okay. So remote sensing does not necessarily mean only the electromagnetic remote sensing. It can be the particle remote sensing also. At the same time, you have in situ observations. What is in situ observation? In situ means at site. So you have embedded your instrument in the environment which you want to study. A few examples are like, say, mass spectrometry, wherein you study the composition of different gases, gas atoms and molecules in a given planetary environment. Or you want to do a seismology. You have kept a seismometer on the surface. So that is in situ observation. Or you're having a charged particle detector or a plasma analysis instrument. So all these instruments are in situ instruments. So depending on the scientific objective, you have to select your instrument. So I can go on speaking on this, but it's not the objective. Only my objective was to tell you that there are two branches, two ways of studying, remote sensing and in situ. And in each of the things, there are a lot of possibilities which you can think of. And there are certain innovative things also what you can think, which you can work out. Now coming to an example, let us see Chandrayaan-2 mission as a case study. So the fundamental question was, how did the solar system evolve? Now, which celestial body will tell you how did the solar system evolve. If you have to go beyond Earth, it is the moon. It's easily accessible, and at the same time, it is airless body. And since it is airless, it didn't undergo much of a chemical weathering. And hence, and also Earth's moon is a natural laboratory to study the solar system. And there is no global magnetic field, so direct detection of the lunar surface, interaction of the lunar surface with solar wind is possible, which you cannot do on Earth because Earth is protected with the geomagnetic field. And a lot of other things you can do, and is very much accessible for orbiter missions, lander rover missions, so on and so forth. So you have chosen your right target. Now the question is, you have to break up the fundamental question, how did the solar system evolve, to certain specific questions. Like, you may be interested to study the bombardment history of the inner solar system. Moon is the record keeper. Or structure and composition of the moon you want to study, which will tell you about the information on the evolution of differentiated planetary bodies like this. So I don't intend to go on reading all this list. What I want to tell you, how to break up the fundamental problem to some specific problems. And from the specific problems, what you get to know what are the domains you have to study. Like, all this gamut can be studied if you study the elemental composition of the surface, you study the mineralogy, you study the hydration features, like whether water is there on moon kind of things, volatile studies on the lunar surface, neutral and ion exosphere you can study, imaging you can do, surface studies you can do. All these things are the domains you are identifying. Now with this, Chandrayaan 2 suite of instruments was selected. So when it came to mineralogy, there were instruments like CLASS, which is basically an X-ray signature detecting instrument, and XSM was an instrument which has to study the sun. So energy from solar X-ray from the sun was studied, and that perturbation caused to moon was studied by the CLASS. So it is a cause-effect dual instrument which told a lot of things about sun, at the same time a lot of things about the surface of the moon. And it had instruments to study the hydration features, like the IIRS, the remote sensing instrument in the infrared region, which could tell about the hydration on the moon surface. A mass spectrometer CH2, which could tell about the water vapor in the moon's exosphere. Similarly, for the study of the surface roughness, you had dual frequency synthetic aperture radar and dual frequency radio science experiment for neutral and ion exosphere. So on and so forth. Then you had imaging instruments called terrain mapping camera 2 and orbital high resolution camera OHRC. So this is how the suite of the instruments of the mission take its shape. Now, what happens after the mission is launched? You have reached your desired target. What after that? Then there is a phase of payload commissioning and verification phase to check whether your instruments are working properly. Then there is a science observation phase wherein you are operating an instrument and observing what is happening around the celestial body. And then you receive the raw data from the instruments and you go on doing higher levels of data generation with the calibration parameters and corrections, so on and so forth, and just lead to publications. So this is how the whole chain works. Now, coming very quickly to the glimpses of our lunar mission. Under the Planetary Exploration Program, ISRO has a lunar exploration program. We started way back in 2008 with the launch of Chandrayaan 1 mission. So it was a typical example of international cooperation, as it carried instruments from multiple space agencies along with Indian instruments. So several discovery class of instruments were made. Discovery class of results came, publications happened. I'm not going to those details, but what has happened, it raised a lot of questions, and which inspired the Chandrayaan 2 mission, which was flown in 2019, which is still in the lunar orbit. The science aspects of Chandrayaan 2 constitute the subject matter of a full-day conference. But here I would just mention here that mission has unambiguously detected the lunar water ice by extending the infrared camera wavelength beyond 3 micron. In Chandrayaan 1, it was 2.8 micron. Now it has gone up to 5 micron and captured unambiguously the absorption feature of the water ice. Among other interesting results are the global mapping of the argon-40 in the lunar exosphere, first of its kind of result, and detection of trace elements like manganese and chromium on the lunar surface. The Chandrayaan-3 mission now is getting ready to study the lunar surface in terms of its elemental composition and other surface studies, which is going to land at the lunar higher latitudes. And also a study is going on to investigate the lunar volatiles from the lunar poles. So this is how the lunar program, India's lunar program, is going on. So apart from Moon, there is a program on exploration of Mars, as you are aware. India's Mars orbiter mission was launched in 2013, which reached the orbit in 2014 with a suite of instruments. The Mars orbiter mission have made significant discoveries in the domain of composition of the Martian exosphere, as well as the aspect of the solar forcing on the Martian atmosphere. And also it has detected something very interesting, which we call very high energetic suprathermal argon-40 atoms, which were somewhat outliers in the other argon-40 atoms which we have seen. And they provided some clues about the escape of the Martian exosphere to space. And the Mars orbiter mission has captured several interesting geological features of Mars surface, including the terrains and the CO2 ice in the polar region, studied the Martian albedo. It also imaged Phobos and Deimos, which are the natural satellites of Mars. And this mission has given opportunity to develop, I must say, not only good science, but also essential technology components like complete autonomy of the spacecraft in a planetary mission, where the spacecraft is not visible from the ground station and the RF distance is also appreciable. 8 to 20 minutes of RF distance is there. So real time, you cannot control your satellite around the Mars. And studies on the future Mars missions are also in progress. Coming to the astronomy venture, I started my lecture by telling the history of the evolution of ISRO, and astronomy played a major role there. And then I told you how did the idea of AstroSat emerged. The AstroSat is still in space. It was launched in 2015. And as I told, it is a multi-wavelength observatory in UV, visible, soft, and hard X-ray. And it has involvement of many premier institutes like TI, EFR, Indian Institute of Astrophysics, IUCAA, RRI, NCRA, to name a few, and space instrumentation and science were the domains where all of these institutions contributed. And it has a suite of instruments called UVIT, Ultraviolet Imaging Telescope, Soft X-ray Telescope, Large Area X-ray Proportional Counters, cadmium zinc telluride imagers, scanning sky monitor. Now, these AstroSat observations have led to several discoveries and exciting results, like discovery of UV photons from earliest galaxies, discovery of phase resolved X-ray polarization in Crab pulsar and X-ray polarization from several gamma ray bursts, and contributed significantly towards solving of the puzzle of a cosmic source being bright in both infrared and UV due to a hidden white dwarf. So AstroSat observations have also led to the detection of evolution of a gamma ray source stuck in a very long flaring state, exhibiting dozens of states of activity, and also to the detection of time-varying prompt emission of the polarization in X-rays in several GRBs, helping in constraining the GRB models. And this is still active, and it is going strong with the participation of the community of astronomers and astrophysicists. Coming to the heliophysics endeavor of ISRO, all of you know about the Aditya L1 mission, which will be the first Indian space mission dedicated to study the sun. This spacecraft will be placed in a halo orbit around the first Lagrangian point of the Sun-Earth system, which is about 1.5 million kilometers away from the Earth. Now, the interesting part is that the first Lagrangian point, or the L1 point, is outside the Earth's magnetosphere. And it is particularly advantageous for observing the solar activities and its effect on space weather. Out of 7 instruments to be carried by this Aditya L1, 4 payloads will remotely monitor the sun, while 3 instruments will conduct in situ studies of the particles and the interplanetary magnetic field sitting at the first Lagrangian point. So Aditya L1 is specifically designed to study the coronal mass ejections events. The X-ray instruments will track the evolution of the solar flares from soft to high energy X-rays, and parameters like the delayed particle spectrum and magnetic field changes also will be measured sitting at L1. And sitting at L1, it can also give you some early warning about the perturbation erupted from Sun to Earth in a lead time of about 30 to 40 minutes. So that is also another preparedness for to be prepared for any space weather events. And this measurement will be vital to space weather modeling efforts, including propagation effects in the inner solar system. So since I am telling about a few upcoming missions, Chandrayaan-3, as I mentioned when I was speaking to you about the lunar missions, the science which we are planning include the study of the thermophysical properties of the lunar surface, lunar seismicity and elemental composition of the lunar surface in the vicinity of the landing site. The spacecraft has a lander module which rover inside, and the lander and the propulsion module. So the instruments are the ILSA for measuring the seismicity, which will be in the lander, the Chaste instrument, as I told, for the thermophysical property investigation of the lunar regolith, the Langmuir probe for the lunar near surface plasma environment, and there is also an instrument, lunar retroreflector array by NASA, for laser ranging to study the Earth-Moon dynamics, the distance between the Earth and Moon will be studied, and lot of inference you can make about the core of the Moon, and this is a very, very interesting domain of study. Now the rover, which will be inside the lander, will carry instruments like alpha particle X-ray spectrometer APXS and laser-induced breakdown spectroscope clips to determine the elemental composition and abundance in the vicinity of the landing site. Now coming to another upcoming mission, which is an astronomy mission, AstroSat, which will also be a unique one as it will decipher polarimetry, spectroscopy, and timing information from the same platform for various bright astronomical sources in the X-ray regime. So it will be the first dedicated Indian satellite for polarization measurement in medium energy X-rays. As you are aware, polarimetry is an important diagnostic tool to study the emission processes that are degenerate with respect to spectroscopic and timing information. So this gives you something additional. And it is going to carry two instruments called POLIX and ASPECT. POLIX is the polarimeter instrument in X-rays, which will provide polarization information in the X-ray range 8 to 30 keV for bright astronomical sources, and ASPECT is X-ray spectrometer, which will provide spectroscopic and timing information in the energy range of 0.8 to 15 kiloelectron volt. Now here at this juncture, I must tell you a very important information, especially the students and faculties who are listening to this lecture. All these space science missions data are accessible in a repository, which is the Indian Space Science Data Center, Belalu, ISSDC. It is the same Belalu, ISSDC, where our deep space network antenna is sitting, 32-meter antenna and 18-meter antenna are sitting, and one more antenna has come up. So these antennas are communicating with the deep space missions, and in that same campus we have our ISSDC Indian Space Science Data Center, which archives all the data from the planetary mission. So I request the students and the faculties, if we have not done so far, please visit the site and see what are the treasures kept there, and it systematically stores all the scientific data and also tells you about some documentations which are archived, telling you about the corrections you may have to do on the data in terms of calibration factors and certain other things. And also it tells you about the the scientists who are working on this, the people who are behind these experiments, if you want to contact them, discuss on any specific issue, we can do that also. And also it keeps a record of the publications which are coming out. So I recommend that you must visit this fantastic work of ISRO. So as I am about to wind up, I must tell you that this upper panel, which you see in this slide, tells about the legacy of the space exploration in India. It provides you a summary of the missions. You might notice that initially there were scientific payloads flown in satellites which were not dedicated for space exploration. From there, ISRO has evolved to send dedicated space science exploration missions, and this journey continues. And in this journey, ISRO looks forward to explore space to study a few more domains like astronomy during quiet and disturbed solar conditions. What I mean quiet and disturbed solar conditions, you are aware that Sun is having an 11-year cycle wherein its activities modulate. And in 2025, we are heading towards another solar maximum. So those eruptive events from the Sun, they get spread over the solar system, and Earth is sitting right there, which is intercepting that energy. And the perturbation is first felt by the upper atmosphere of Earth. And if you study the upper atmosphere of Earth, which we call aeronomy study, you see the effects which are happening on the atmosphere-thermosphere system of the Earth. So that is one area of study, and many of you are aware that on 10th of May, that is day before yesterday, we had one day long program with all the academia and representatives from the ministries on a concept of a mission called Disha. Also, the Venusian science is another area, and also the connection of Sun with Venus. So, as many of you are aware, on 4th of May in this month, we had one-day meeting on scientific prospects of a Venusian mission, sending an orbital mission to planet Venus. We had a discussion by roping in the wisdom of academia and institutes of the country. The people, many of the scientists who are working on Earth-based science are extending their knowledge to the other planets. Okay, so that's how the community is now getting built up. Also, integrated space weather study. That is, when I say integrated space weather study, I say you are having the heliophysics mission to study what is happening on Sun, and you're having astronomy missions to study what is happening in terms of the effects on the upper atmosphere. At the same time, you're having the ground-based networks, which I have not spoken in my lecture, which are studying what is happening to the ionosphere from sounding them from the bottom. Okay, and also studying the scintillations by capturing the phase changes in the GPS signals, which are received by the GPS receivers. So it is a combined effort with ground-based networks and astronomy satellites and heliophysics missions. Also the solar observatories which are on ground. Okay, that is what I mean as the integrated space weather study. And also the study science from space, as you are aware, Gaganyaan is coming up, the human space mission. It is also a potential platform for doing science from space, not only science of space, but the science from space, wherein you can use space as a natural laboratory to do fundamental science. A lot of scientific concepts you can prove if you are sending scientific experiments where a trained astronaut who is also a scientist sits there and does the platform, or even if a scientist does not sit. If it is an unmanned Gaganyaan, also you can have plan for an experiment wherein you will retrieve the module on ground, and after retrieving the module, you can infer a lot of science from there. And it embraces not only space science, also material science, the aspects of biology, not only biology, but it's called the science of the, not only astrobiology, it is science of the scales, growing artificial organs in space. Okay, all these things are open once you have such a platform, which offers you macrogravity and peculiar conditions in space which you cannot get otherwise. So space is not only the astronomical or celestial bodies, a lot of other things also we can do. using space, using the microgravity platform. Now, coming to the almost the end of my presentation, I must here mention the Indian Space Exploration Program synergizes the contributions from the Indian institutes and academia, and international collaborations are in place for joint scientific programs in the forms of, it could be joint development of payloads or say scientific working groups and any other forms of cooperation. Now, with these, India's space science and exploration program offers opportunities for the scientific community to expand its research horizons and probe to the depth of the unsolved problems of space science. Now, I will summarize by telling you the take-home messages what I have told you, especially my dear students, who many of you must have come to know many things about our Indian space program. To summarize the whole thing for you, see, India's space science exploration, it includes the exploration of the solar system bodies, which we call the planetary exploration, also the physics of the sun, heliophysics and space weather, including astronomy, astrophysics, including exoplanets. The exoplanets means the planets which are in some other solar system. And we have discussed about a few missions, Chandrayaan 1 and 2. We also have discussed about our Mars orbiter mission, told you about a few results. And we have also discussed a few about AstroSats. And what we have not covered in this lecture is very important to know that this is not the entirety I have presented to you, not possible also in this time. The missions in pipeline, anyway, if you visit the ISRO website, it tells about a few of them. And ground-based space science, whatever we are doing, that itself is a big subject, which I could not cover here. My apologies. And serendipitous observations, serendipity, you wanted to do something, but you got something else unexpectedly, okay? Some examples are signs of the sun from moon. With the lunar study, you have sent instrument to study the sun, and lot of insights have come about the solar macroflares, and also, which tells a lot of clues about the coronal heating problem from the XSM instrument. So objective is to study the moon, but the instrument carried a device to study the sun, which studied some very good aspects of sun, which got global impetus in terms of very good publications. So I request you to visit the ISRO website, www.isro.gov.in, wherein you will get a section called, that story of the week. In this story of the week, all these discoveries are mentioned, which I could not cover. And also, a recent discovery was in the Mars mission, the study of the solar corona using the Mars orbiter mission. It was intended to study Mars, but it is also studying what is happening in the solar corona by studying the signal which is propagating through the solar corona and the perturbations which it is undergoing in terms of the space difference. So those information you will get if you make a habit to visit ISRO website. Okay, so please visit ISRO website on a regular basis and see what all are happening. And engagement with academia and institutes, I have already told you. And promotion of space science activities is one area, and international cooperation I also have told. Space data are also available to public, which I also have informed. So before I conclude, I must make a mention of a hymn from Rigveda, which tells, Atmana Mokshartha Jagat Hitaya Cha. Atmana Mokshartha means salvation for one's own self. Okay, and Jagat Hitaya Cha, you understand that something good to be done for all of the world, and these are happening together. That's what joy is coming. So Indian Space Program is doing that. Indian Space Program, every contribution to the space mission or any ground-based observation is giving rise to the wealth of knowledge, and that is how we are able to appreciate the interconnectedness of the macrocosm. That is how this Atmana Mokshartha part is coming. And coming to Jagat Hitaya, which I have not explained in this short presentation, lot of societal applications of ISRO touching lives of the earthlings, that is another domain. So with all of your good wishes, let this journey continue and let us do very good science. Thank you very much for your kind attention. That's all from my side. Thank you.
Thank you, Tirtha, for this wonderful exposition of the various space science activities of the Indian Space Research Organization. I hope that students have got a broad overview of how ISRO plans, executes, and implements space missions, and also of the exciting opportunities that is coming up in the near future. So what I'll do now is I will allow people about 30 seconds to ask questions and post questions in YouTube as well as in Gmeet. And I will select some questions which are suitable for you, and then I will ask them. So let me just give about a few, half a minute for questions to come up.
Sure.
Okay, so there is one question from K. Ramesh from SPL, who says, "Thank you for your excellent talk. I'm curious to know if there is a dedicated mission to measure atmospheric drag in the upper atmosphere due to the anthropogenic changes in the lower atmosphere."
Oh, that's a very good question. See, I must tell you, first of all, there is no dedicated mission to measure the drag only. Okay, so, but at the same time, we can measure the drag because of the presence of the accelerometers in the satellites. So from basic calculations, if you have a satellite at this altitude,
I'm in a talk that
and
I'm
suppose
hosting
there
for
is
ISRO, so I have to finish
no
that.
atmosphere,
So give me.
that the satellite would have been at a given time that we call the satellite ephemeris. That is ideal. But because of the drag, the satellite is elsewhere. Okay. From this difference between the ideal and real orbital determination, which we call OD, of the satellite, from this anomaly, and at the same time merging the information of the orientation of the satellite, that is the projected area along the velocity vector, we can find out how much is the drag. Okay, and you're having the accelerometer information, so that tells you. So that is not a dedicated mission, first of all. And the second part of your question is because of anthropogenic effect. No, we have not done anything like that so far. And anyway, thank you for your good question.
If I may also add to Tirtha's response to that question, there is a dedicated suite of satellites from the European Space Agency. These are called the swarm satellites,
Right.
which actually provide information on drag on a real-time basis, and the data is available for anyone in the world to analyze.
Right.
So let me now look at the other few questions that are coming in, Tirtha, and I'll just read it out for them.
One question is
Okay.
Okay, yeah.
So there's a question from Rakesh Narwa, which says that thank you for your detailed presentation. I'm using data from ISSDC as I'm a registered user. I'm guiding students for their PhD on Chandrayaan-2. Can I give the data to my students for their PhD studies?
Yes, ISSDC data as you are accessing as a registered user, and you are using for academic reasons. Okay, so definitely the answer is yes.
Okay, so we have some questions from YouTube. Let me ask them. One from Pratim Chakraborty, who asks, what is the probable date of final execution, by which I guess he means the launch of the Aditya L1 mission?
Okay, so those details are also will be available in the ISRO website in due course of time, which I may not be in a position to answer in this forum. But soon.
Okay. The other question, also from Pradeep Chakraborty, is what were the shortfalls of Chandrayaan 2 how will the shortfalls be rectified for the next Chandrayaan mission?
Okay, shortfall, when I say it is a continuous improvement process, uh, like in Chandrayaan 1. So I will not give a definite answer because that will not make sense, but I will tell you how these things are done. See, Chandrayaan 2 instruments are chosen based on the scientific observations in Chandrayaan 1 and the certain lessons we have learned from Chandrayaan 1. Okay, and this has prompted us to make some changes in the specifications. One such example I will tell you, as I have mentioned in my presentation, the range of the infrared spectroscope was up to 2.8 micron. But there in the 2.8 micron range, the moon mineralogy mapper could capture the only 1/2 of the absorption spectrum of the hydroxyl radical. Water vapor, not water vapor, waterized H2O signature could not be captured because it was coming a bit beyond about 3 microns. So taking lessons from there, we have done improvement over the wavelength range of this IR spectrometer, which is flying in Chandrayaan 2. So like that, when we are planning for the next missions, so orbiter-based missions, we are taking into account the science which are coming out from the previous missions and whether any interesting feature we are missing because of any shortfall of the specification of the instrument, whether extending the dynamic range helps, or whether improving the resolution, whether it is a spatial resolution in case of imaging instruments or spectral resolution in case of, say, remote sensing instruments, or mass resolution in case of mass spectrometric instrument helps.
So,
okay, this way that thing continues to happen. I hope I could address without going to the specifics how this improvisation happens. Okay, the same wisdom will be passed on when we plan for the next mission. So this is how these things happen.
okay, so one more question from Mitali Unawane from YouTube. How are teams and members selected for work on ISRO missions?
Okay, what happens is if you see the different centers of ISRO, there are several centers which are having different expertise. Some centers are having expertise for developing instruments for imaging. Okay, like Space Application Center, Ahmedabad. They also have the expertise of preparing instruments for infrared-based observations of the ground. Or there is a center called LEOS, Laboratory for Electro-Optic System. They are experts in electro-optic payloads. Okay, and you're having also centers for URL Satellite Center. They have expertise in, say, X-ray astronomy or space physics laboratory. They're having expertise in some other domain. So depending on the kind of observation you want to do, I started from a fundamental question and I have shown you how to select your instruments. So depending on the instruments you are choosing, the people behind those instruments also become a part of the mission in terms of the scientific instruments. But mission is not only scientific instrument, mission is beyond that. Mission is starting from the basic mission design, right? So when you come to the mission design, there is a dedicated team which does this flight dynamics computations and coming to the optimum mission configuration. So when I say the mission configuration entails how will be the orbit, how many earthbound orbits you will have, then you will have what kind of a transfer orbit and captured orbit, all these things. So when I say a mission, it is not only about scientific instruments, wherein I told, depending on the instruments, you put the expertise. At the same time, you're having a teams which work on the mission design. So that is how the things happen. But at the same time, I would also like to tell you a very important aspect in this regard. Team for a mission or a space mission does not mean it only has to be from the ISRO Department of Space. Our chairman also is very much encouraging us that you should also synergize the wisdom which is coming from the academia and institutes of your country. And also, if possible, you can learn from the other space missions also. So rope the academia and institutes in right from the beginning of the inception of the mission. Okay, that new era has started, and how to make them your co-passenger in your entire journey before launch, at the same time after launch, to do maximum science of it. So that is how the mission team builds up and they carry the baton. I hope I could answer your question. Thank you very much for the question.
Okay, we have some questions related to the Aditya mission. One from YouTube and another in the Meet. I'll combine the two questions and ask you questions. How is Lagrange point? Well, they don't specify which Lagrange point, but it is Lagrange point L1. So how is Lagrange point helpful for studying the sun? And the related question is, how is ISRO preparing to protect the Aditya mission or any other mission from severe space weather events?
Okay, so coming to the question, see Lagrange point 1, as you all know, there are 5 Lagrange points. So specifically, Lagrange point 1 is the one which is situated, if you draw a line between Earth and Sun. So Lagrange point 1 lies on that straight line, which is closer to Earth. And incidentally, that point happens to be beyond the magnetosphere. Okay. Now, Lagrange point 1 is the point where the gravitational forces of Earth and Sun, they cancel. So this is such a region of space wherein the forces are getting balanced, and around that Lagrange point you are having a halo orbit which sustains itself, and being outside the magnetosphere, you are studying the effects of the energetic particles, charged particles, which are coming from the sun without getting them affected by the magnetosphere. Okay, so you are beyond the shield of the Earth's magnetosphere, and you are studying. So that is a very good way to study when you have to study the charged particles, which are otherwise deflected by the Earth's magnetic field. And coming to the second question,
did he lose Tirtha? I'm not hearing him.
Yes, I think his internet is not stable.
Internet here is unstable, or so we have had a disruption. I think Tirtha has lost his connection. We'll wait for him to sign back so he can complete the Tirtha, we have lost you. Acha. Is there any reasonable chance that you can? We'll give it a minute or two. Acha, okay, fine. Acha, okay, all right. I will just then conclude. Okay, all right. Thanks, Tirtha. ठीक है. Okay, okay, all right, okay. Okay, folks. Unfortunately, there has been an internet outage at Tirtha Pratim Das's end. So we have to conclude this talk here. He was about to respond to, I think, the last question. He did mention about the importance of Lagrange point L1, which provides continuous observations, the possibility of continuous observations of the sun without being eclipsed by the Earth, which happens for satellites on a polar orbit or low Earth orbit often. So this is a point where the gravitational field of the sun and the earth cancels out, and therefore a satellite parked there really moves along with the sun-earth line during the revolution of the earth around the sun. So it has a continuous view of the sun and also has continuous telemetry link with the earth, which is the advantage of having sun observing missions at Lagrange point L1. There was a question on how is ISRO preparing to shield satellites such as Aditya or other satellites from space weather. So I'll briefly respond to that. In fact, the Aditya L1 satellite is a satellite which observes the genesis of space weather, which occurs due to the activity of the sun. So the Aditya L1 satellite is good to observe flares and this large scale solar storms known as coronal mass ejections, which initiate at the sun and sometimes can impact the Earth's magnetosphere, giving rise to geomagnetic storms and severe space environmental effects, which impact satellites and technologies. So Aditya L1 has the mechanism to observe the sun, but also to make in situ or local measurements of the space environmental conditions just outside of Earth at Lagrange point L1 before they impact the Earth. And so information from the Aditya L1 satellite will help us in assessing the space environmental conditions. For preparing our satellite systems and creating mitigation techniques for space weather, one needs advanced predictions. And advanced predictions are only possible through a synergy between observations of the sun and dynamical models, which some organizations around the world, like the NOAA Space Weather Prediction Center, as well as our own institute, the Center of Extensive Space Sciences India, here in India, are involved in. I'd like to conclude the lecture here. Once again, thank you very much for all of you for attending this first in the series of the public lectures that has been planned in association with the National Space Science Symposium. And we hope to have you back again for the next lecture in our series, which will be announced in due course. Have a good evening and all the best to all of you.